The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Without any further ado, I would like to invite our first speaker, Caroline Hansen. Caroline is a professor at the University of Waterloo, Ontario, Canada. And the title of her talk is the Tribute Paper to Brian Hope. Tribute to Brian Hope, Ph.D. Professional Engineer, Fellow ACI. Is that Caroline?
It's an honor and a pleasure for me to present a tribute to Brian Hope. Unfortunately, Brian isn't able to be with us today for health reasons, but we expect to see him fit and raring to go at the Toronto meeting in the fall. So anyway, I'm sorry he won't be with us today. If you type Brian Hope into Google, the first thing that comes up says Brian Hope, comedian, Kingston, Ontario. And this is the logo. And I thought it was actually pretty good. You know, the disintegrating R and the cracks in the N were rather fitting for Brian, who spent his life looking at deterioration of materials. But in fact, this is not our Brian Hope, despite the fact that our Brian Hope does live in Kingston, Ontario. This is our Brian Hope, or as he was on his first visit to Canada back in, I can't remember when. But anyway, that was the Brian Hope then, and this is the Brian Hope we know and love now. Brian is a Professor Emeritus at the Queen's University in Kingston, Ontario. He was an exceptional supervisor, mentor, and teacher, a collaborator extraordinaire, an excellent engineer and researcher, but he was also a family man and a hobbyist. So I'm going to go through each of those aspects of Brian one by one. As a teacher, supervisor, and mentor, starting with teaching, he was the first recipient of Queen's University's Golden Apple Award, which is the highest award that the university gives for teaching. He received that in 1971, and he received it again in 1992, showing that, in fact, he had not lost his edge over all those years. He supervised 23 graduate students, 11 on aspects of rebar corrosion, the subject of the 222 committee. He always took the trouble to explain to his technicians why they were doing what they were doing, rather than just asking them to do something without any explanation. And this was very well received by the technicians, and you see later on how important this was. I was co-supervisor with Brian of 8 different students, so I know of what I speak when I said he was a fantastic supervisor. But I want to use the words of one of Brian's first students, David Manning. I do want to add that Brian and Nita were extremely generous to Julia and myself. Coming from the aloofness of an English university, our relationship was a breath of fresh air. I arrived at Queen's in 1968. Brian took Noel Brown and me, his 2 graduate students at the time, to an ACI one-day seminar in Ottawa in December 1968. In April 1969, the ACI convention was in Chicago, and Brian created considerable controversy within the civil engineering department by paying for me and Noel to attend the convention. This was the first time a graduate student had ever been funded to attend a conference. While I was at Queen's from 1968 to 1972, he entertained all his graduate students at his home, and he provided support to our families far beyond his academic responsibilities. That's the kind of supervisor he was. As a collaborator, several of our co-supervised students used to say to us, "How can the two of you argue so loudly and vehemently without getting your feathers ruffled? And then still remain good friends at the end of it?" Well, that was the wonderful thing about having Brian as a collaborator. We could and did fight over everything. But it was always about an issue, excuse me, never taken personally. And the result was that we did a much better work from being able to say frankly to each other what we thought. So as an engineer and researcher, these are some of the areas of his endeavors. I'm not going to go read them out to you because you can read them far faster than I can actually read them out loud, but I'm going to go through them, some of them, one by one. First of all, chloride extraction from concrete. As you'll hear from David Trejo later this afternoon, there has been considerable discussion among the different committees of ACI on how much chloride should be permitted in the ingredients, the components that go into concrete, to make sure that the steel in the concrete does not begin to corrode. Brian found out, what is obvious to everybody, that the more finely divided the particles, the more chloride is extracted. But this was the first measurement of that and the first quantitative evaluation. Well, of course, if you think about concrete in practice, the aggregates are not ground, and yet in the lab, we grind them to get the chlorides out. So what he was trying to do was to figure out how much chloride was coming out of the aggregates, or would come out of the aggregates, and cause problems for the steel in practice as solid aggregate particles. So he introduced the Soxhlet method of extraction and found that you can extract from half-inch chunks of concrete all of the chloride that's going to be available throughout the life of the structure, predicted, of course, within a 24-hour period. Well, I'm sure many of you don't know what the Soxhlet method is, so I'll quickly explain it to you. The specimen is put into a porous container here. And the solution, and if you want to have water extraction, that would be water. If you want to have acid extraction, that would be acid. It's put into here. This is heated up. It evaporates up into this condenser area here and condenses out and drips into this area where the specimen is. When this becomes full, it will overflow and go back into the solution and so concentrate. And over a 24-hour period, you get out all the chloride that's ever likely to come out. This was accepted by the ACI 222 committee and is now one of the standard practices that's recommended for extracting chlorides. Well, of course, if you're talking about chlorides, we also need to know what the chloride threshold value is. The chloride concentration necessary to cause corrosion. Well, today, of course, there are thousands and thousands of experiments that have been done trying to measure the chloride threshold extraction. But this was one of the earlier ones. This is in 1987. And what he was looking at here was for admixed chlorides and chloride-containing aggregates. And he studied this by looking at linear polarization resistance, electrochemical impedance spectroscopy, gravimetry, and visual inspection. And he was one of the first investigators to link corrosion activity with the resistivity of the concrete. He was also one of the first. At this time, there were probably about three investigators around the world using EIS, electrochemical impedance spectroscopy, to study corrosion of steel in concrete. And this, just to give you an example, this is the one with admixed chlorides. This is the Nyquist plot for admixed chlorides, and you can see there's not a large diffusion component, which is this one here, because the chlorides are available in the solution having been admixed. When the chlorides were present in the aggregate, as the contaminated aggregate, there's a much, much greater component of the diffusion that's got to contribute to the threshold value. The next study he did was corrosion inhibitors, and he looked at corrosion inhibitors from the point of view of three different aspects. One of which was with Sally Thompson here to look at the possibility to see whether you could apply the inhibitor to the surface to halt ongoing corrosion, and if you did, was it going to be beneficial or detrimental to the concrete? Unfortunately, the photograph is awful because the photograph came from 1980-something or other, prior to electronic submissions, so this is a scanned-in photograph. But what he found was, in this case, when the concrete was soaked in a mixture of calcium nitrite and sodium molybdate, it disintegrated within 2 weeks. Not such a great idea. The other aspects that he looked at were that he found, or he and his students, found that the inhibitors were very effective in delaying the onset of corrosion when the concrete was exposed to chlorides from the outside. However, it did not have much effect on the corrosion rate after initiation of corrosion, and if you tested the steel in pore solution containing inhibitors, then there was very, very little effect, if any. So this suggests, of course, that unlike the hypotheses of the day, the inhibitors were not influencing the passive film on the steel, but influencing the ingress of the chlorides into the concrete. Another aspect of his work was in cathodic protection. This was one of the experiments he did early on, where he built looked at the cathodic protection of a quotes, unquotes, post-tension beam. This is the beam. He had what he called deck rebar up here, and the post-tension cable, duct was here, but instead of having post-tension cable, he had small coupons from which he could measure corrosion. And he was applying a current from a conductive paint from the surface and measuring the proportion of the current that went to the deck rebar, to the duct, and to these embedded probes. And this was the plot of instant off potential. It's written as a negative, so this is minus 1,000, minus 800, versus the applied current density. And this is the area here, about 1,100, with a more negative voltage than this, hydrogen is evolved. So he was recommending to the ministry and to other Ministry of Transportation and other authorities that the current density that should be applied is this approximately linear region here. However, all the advice you can give is to naught if people don't follow it. At this time, he was advising or working with the Ministry of Transportation to design cathodic protection systems. And there was one system he was working on of a bridge over a railway in Kingston, Ontario. And after a few years, and he specified, never let the potential get to more negative than 1 volt on the copper sulfate scale. So he went back a few years later to inspect this and check up that everything was going fine, and found the potential was minus 2 volts. He got hold of the engineer and said, "What are you doing? The specification said minus 1 volt. And the engineer looked at him and said, if 1 volt's good, 2 volts must be twice as good. That was one of the examples where Brian learnt that it's not enough to know what to do, you have to know why you're doing it. And that was one of his philosophies for the rest of his professional career. Another aspect of this work was it's been generally agreed that high-strength, highly stressed steel is easily susceptible to hydrogen embrittlement. But it's also generally thought that the regular mild steel that's used for rebar is not susceptible to hydrogen embrittlement. These were his data on mild steel. And you can see that this is the applied current density. I think it was applied for 2 weeks. And you can see that he was applying to 40% of the UTS, ultimate tensile strength. This dropped from about 250 down to about 125. In other words, it was 50% less. Similarly with the yield stress. So this was the first time that people had actually discovered that ordinary, everyday rebar can in fact be susceptible to embrittlement. Going from cathodic protection to electrochemical chloride extraction, he attacked these, I think he had 11 different projects on this topic, varying from the influence of multiple rebar mats and mat configuration on the effectiveness of chloride extraction to the chemistry and microstructure of the concrete after chloride extraction. And this is one of the projects that he had. In this case, we have there's a cylinder of concrete which is partially immersed in a solution. This is the cathode, and this is the anode, and a current is applied between them. And after a certain period of time, this part and this part were tested for both density and for compressive stress. And as far as the density is concerned, you can see that the cylinders were upright, they were cast upright, and so there must have been some bleeding here, because to start with, there was with no current applied, there was a difference in the density of the anode and cathode area, the cathode being less dense. But nevertheless, with the current, there was a slight increase in density for both areas, but in this case, with the compressive stress, the stress in the cathodic area decreased significantly more than the strength in the anodic area. That was just one of many of the projects that he was involved in. Finally, on this part of the presentation, I have to admit I drew these two diagrams incorrectly, so bear with me. Stainless steel has been used over the last probably decade or so, as a remediation or a prevention of corrosion in those areas of the concrete structure which are most severely exposed or exposed to the most severe environments. And the idea has been, let's use stainless steel for those parts and use ordinary mild steel black rebar for the parts that are less exposed to less severe environments. The concern, though, was the interaction between the stainless steel and the black steel. Is there any galvanic interaction between them? So, for example, if you have stainless steel at the top and black at the bottom, and the chlorides should go all the way down to here, would the fact that the black steel is connected to the stainless steel provide a greater corrosion rate for the black steel than it would do if it connected to black steel? In fact, it's the absolute opposite. And until this work, the authorities throughout North America were electrically insulating the joints between the black steel and the stainless steel. And that, of course, is very costly, both in time and money. And what he found was this reaction, which I've highlighted here, it's the same one as here. This should have been all in black, by the way. This reaction, which is the cathodic reaction, it's the cathodic reaction, the reduction of oxygen, which drives the corrosion rate. And stainless steel has a much lower exchange current density. So the efficiency of this reaction on stainless steel is much less than it is on black steel. So if you connect black steel in a chloride environment to stainless steel in or not a chloride environment, the corrosion rate would actually be less than if you connected it to another piece of black steel in a non-chloride environment. And that has saved the authorities a huge amount of money. This experiment's since been repeated in Italy and various other places. But Brian was not just a professor. He was also a family man, is also a family man. This was taken some years ago in Hawaii, a holiday family, with Anita, his wife, who also worked at Queen's University. She was in the administration. And their two sons, John and Jim. John is now a successful physiotherapist, and he and his wife have 3 children, making Brian and Anita very proud grandparents. And Jim is extremely, I believe, successful car designer. He spent his time at GM in Detroit and then went over to GM in Germany and is now with a GM affiliate in China as one of their top car designers. Oh, this is another picture of Brian as a happy father in Australia some years ago, shall we say. But he has another side to him. He liked his toys. This was his pride and joy at the time. 1972 Fiat Spider. He also had his hobbies, one of which was to collect Depression-era glass. And he was for some time a member of the Tiffany Glass Association of North America. Another one, very surprising, was dressmaking. He approached this not from the idea of creativity in the dress, but figuring out how the patterns worked and how you got from there to something that was three-dimensional. And presumably he used his experience with his pattern making when he drew up the architecture for his house. He designed and built a fantastic house in Kingston. And of course, the excuse of having two sons was always a good one for building model railways. So I'd like to finish by saying thank you, Brian, for all your contributions to the profession and your friendship and mentoring to the people who've worked with you. This was taken on a summer work term in Norway and developed his affection for the wildlife. I don't know how many of you noticed this this little fellow sitting on his shoulder here. Thank you very much.
Thank you.
Thank you.